So we just finished talking about the ROC curves at a very superficial level. But the benefit should be clear. It gives you a very detailed overview about the capabilities of your classifier with respect to both types of errors you can commit, the misdetections and the false alarms. That was the material I wanted to show you regarding how can you assess a classifier. So if you go to classification, these are methods you can use to assess the performance of these, besides the typical and infamous accuracy. If we go towards not classification but regression models, so we have to evaluate numerical predictions, we have a different set of methods we can use. Basically, we saw one and we even implemented it last week. Very popular, the mean squared error, MSE. We also saw it earlier today. This is the one where we have the really nice formula for the bias variance trade-off, where it's just a sum of the three components. The specific thing about the mean squared error is we calculate the error, so the difference between our prediction and the true numeric value, we square it. Squaring, as we discussed last week, has the influence that we punish further deviation, larger deviations, much larger, over proportional. But that comes with a downside. It usually means that if we have outliers in our data set, this will completely dominate the error, which is a problem. So if we want an error measure that is less, like it's a problem in that way that we know that, and in order to get good, like meaningful values out of a mean squared error measure, we would have to pre-process our data in order to get rid of outliers beforehand. If we don't want or don't can do this pre-processing, we should rather go for a figure of merit that is less prone to outliers, that is less sensitive to it. And an example would be, for example, instead of squaring the error here, what makes the outliers that are much larger, we could calculate, where is it, the mean absolute error. So we just take the absolute value of the difference of the error. Here we punish large and small errors completely the same way, so it's less prone to outliers. And we'll talk a little bit about this thing when we talk about ensemble methods, I think in 2 weeks. Another interesting thing could be to talk about relative errors. For example, maybe if you would have to predict it 500 and you predicted 550, so we were 10% off, is equally bad or good than if you had to predict 5 and you were 0.5 off. Maybe that's the same in your application, from your application logic. So you should actually measure relative errors if that is the case in your application. So you see, calculating errors has something to do with what do you want to achieve in the end. If you know that something like that the scale of your values doesn't play a big role, it's the how many percentage points am I off, then you should really measure that. You should plug a measure in here that is informative with respect to your application. So, with so many and lots more of examples what you could measure, which one in the end should you measure? Here's an example of 4 different algorithms and 5 different measurements. Same algorithm, always the same algorithms, always the same training and test data, just different ways of calculating the errors. What can we say regarding this table? Which one is the best? We can probably say that D has the lowest error rates amongst all the measures. So it's consistently a better one than the others. And C is consistently the second. But is A better than B, or is it the other way around? Correlation coefficient says they're somehow comparable. Mean absolute error says A has a little bit more error. Root relative squared error, B has a much larger error. So which one is better now? what I learned in practice is that it's a good thing to implement or use all the error measures that you can get a hold of, calculate them all, just lock them away with your evaluation scripts that do all the evaluation for you, and choose at the very end which metrics you rely on, which one you report, which one faithfully represent what you found out. The worst thing you can do is invest lots of compute time, like months of compute, into calculating measurements and in the end finding out that it was a wrong figure of merit that you computed. So compute them all and in the end look which one will you report. Good thing is, in the end it doesn't matter too much, given that A, you report the same things other people report as well. Like if everybody's in your field is reporting mean squared error and you are reporting something else, people cannot compare it. That's bad. You should strive for being comparable. Even if you say, this is a bad measure for my thing, for my problem, just report it anyway. And give the one you would much rather like to give, just give it additional. Yeah, but it doesn't matter too much as long as you are comparable. Just do them all. Regarding clustering, if you want to assess the quality of clustering, it depends a little bit if it is really an unsupervised task, so you don't know actually what is in your data, or you have some ground truth and you just regard it as a clustering task. If you have no labels at all, you're basically bound to visual methods that visualize the clustering, and then you can look at the human at the visualization and say, that looks very good. All the things with the same color are the same region and it's not too much intertwined. Looks like a very good clustering. Here it somehow goes together, it's not well separated. I would prefer this clustering over this. But it's not a numerical measure. It's a visual analysis. Same with the so-called dendrogram. That is a result of a hierarchical clustering. If I see here all the things of the same class belong together, and they are merged before everything else is merged to it, looks like a good clustering. If this all goes durcheinander, is mixed up, you would trust a little less in that method. If you have ground truth, of course, here ground truth is encoded in colors, but you would still think this is a good clustering if you don't see all the colors. Probably, because you see here some separation. Okay, it's better with the colors, I agree. If you have ground truth available, if you know of the data points, which one should cluster together. For example, because you want to cluster images of faces by identity. You usually know which person is it. But you use a clustering algorithm to do it because you do not want to classify hundreds of thousands of people. You can actually calculate measures like the RAND index or a measure called purity that in the end tell you an overall assessment of the complete clustering and of every single cluster. So if you come into the situation where you have to evaluate clusterings, you can look deeper into that. I don't think we need to discuss it. If you don't mind. Main message here, there are ways to evaluate clusterings, and you can look here if you need to do it. So let's move into our final part of the lecture. How do we select among competing models? I threw quite some material out of the lecture and put it into the appendix to make it a little shorter, to focus on the very important stuff. There's lots of interesting stuff in the appendix, so please have a look. Lots of work went into it before I kicked it out again. When thinking about that, we are actually answering these two questions. On what basis could we favor one algorithm over the other? What can we use as a basis for judgment? And given that we now have selected one model over the competitors, how probable is it that this method we chose actually really is the best one? Is there a probability that one that appeared to be less good actually is better? We will talk about both things and how we can do that. So, of course, when we talk about selecting a model, we come again to the question, is there a best model? And theoretically, we have answered it already in lecture 1. No, there's no such thing then. A generally best model. There was a no free lunch theorem that basically says, given all the possible problems in the world, no algorithm has any chance to be better than any other. They all have their ups and downs, depends on the problem. There are empirical studies that confirm that. For example, this rather old one, so that is before the deep learning age. But it's still very interesting because most of the results hold. So still just does not have a deep learning model in it. What did they do? They tested very good Vertreter. What is Vertreter in English? Thank you very much. They took very well accepted representatives of certain classes of algorithms and very, very different data sets and trained the best version of the algorithm they could, and then they ranked it. And here in that table, basically, they are ordered by how well did they do on average over all the different problems. And these were really different problems, like small numerical problems, problems with categorical data, problems with text data, a very good mix of what you have in shallow learning, I would say. And this is now the ordered list of how well did the things do. And we have here boosted decision trees at the very top. We will look at it in the lecture on ensembles in 2 weeks, I guess. We have random forest, which is an instance of an ensemble of decision trees again. We have another ensemble of decision trees here, and we have support vector machines. Ensembles of decision trees and support vector machines, this is what you can still say today, are very good instances of out-of-the-box models. They don't work well everywhere, but they are usually a very simple and very good try. And they don't have much hyperparameters who can train them easily. Neural networks in the not very deep version are also in the table, and you can assume that they could do better when you have the ability to have some layers and the data permits. But you also see there are some other methods very, very much down here that were not very good on most of the tasks. I'm actually not completely sure without reading that what the numbers represent, but given that this is the best algorithm, I think having high numbers here on many tasks is a good thing. The naive Bayes is low numbers almost everywhere, but there is one task it's particularly good at. I suppose that was text classification for spam and non-spam. Naive Bayes does very, very well there, much better than all the out-of-the-box very good methods. So what do we learn from it? There's no such thing than a best algorithm. Every algorithm is somehow good to have in the portfolio, but there are some algorithms that are very valid candidates for let's do a first try. So, again, how can we choose among different models? Excuse me. Who knows the maximum likelihood principle? Heard the name already, maximum likelihood. Who could explain it? There's probably much more to say about the maximum likelihood principle than is on that slide. But you can use it, and you use it a lot in machine learning, to both optimize hyperparameters and in the end select a model. So what is behind it? And I call it here simplistic model selection because we will see more sophisticated methods in the next slides. Usually, when we want to select a specific hypothesis out of our hypothesis space, which means we choose different instantiations of the hyperparameters, we do that at least implicitly by the maximum likelihood principle. We calculate by the figures of merit we just saw how well does a specific instance work, and we take the one that works best, maximum likelihood. If really a likelihood comes out of the approach, this is actually explicitly maximum likelihood. Usually it's not explicitly a likelihood. Then we somehow implicitly, by the same principle, we take just the best, given the current knowledge we have. In terms of mathematical jargon, what we do is we maximize the likelihood, probability, of the data given that it has been created by a current model and its current parameterization trained on that data. We want to find parameters so that the model looks as a better generator of our data set. This is what maximum likelihood in principle means. Of course, this is not taking into account all the information we could have. It takes into account all the data we have. Nice. It takes into account the likelihood that we can calculate how probable is this data given it has been created by the model we just built, but it's somehow a little bit from the wrong side. So maximum likelihood actually doesn't use all the data, all the information that could be around. What information is missing? The information that we could have know from a priori. How likely is the data? How likely is that specific parameterization? Without respect to the rest. This information is missing, the a priori information. Luckily, there is a well-known theorem that can convert between prior knowledge, a priori information, and likelihoods, a posteriori information in the end. These two are not equal. A priori information, likelihoods, and a posteriori information. Information take likelihoods that take into account all information we have, the likelihoods plus the a priori information we have about the hypothesis itself and the data itself. And this is Bayes' theory. Bayes, probably know this guy. Reverend Thomas Bayes was a pastor, I would say, or priest, you call it that, who came up with that theory by thinking about who's putting what into the offering he collected in his church. So, Bayes' theorem tells you you can take the likelihood, multiply it by the a priori information you have on this specific hypothesis, and divide by the a priori information you have on the data set itself. How likely is that specific hypothesis, and how likely is that specific data set? And this is actually all the information you could have, and you could in principle take into account to take the decision, how likely is my model given I observed this data. And this is what you actually want to know. You don't want to know how likely is my data given the model. You want to know the other thing around. You want to know that. So Bayes' rule tells you you can calculate that from the result of the classification. Now you have to know these two terms, you can convert it. That makes lots of sense. For example, if I have, again, these data points here, and I put in green a new model into it, a new regression line. How likely is that line in itself? Hard to tell. You're completely right. But in comparison to which one is more likely a priori without seeing any data? The very jagged curve here looks a little bit more fancy, looks a little bit more less common. There are actually such things as a priori likelihoods of specific models. Some models are per se, without a specific data set, more likely or unlikely than others. So if you would have this information, it would actually be really helpful, and this is what Bayes' rule tells you. But actually, in machine learning, people are a little lazy. So they find out, the data is the same for all possible hypotheses I test, so I divide by the same number here, so we can just ignore it. Because it's just a factor that doesn't affect the ranking of the results. So you ignore this term, the likelihood of the training data. And it's hard to estimate actually the a priori likelihood of the model itself, so you just ignore it. which basically makes the a posteriori likelihood, the so-called maximum a posteriori hypothesis, approximately the same than the maximum likelihood hypothesis. Which then, and this is basically the reasoning you often see in machine learning. This is what you should do, this is what you do in the end, and this is why maximum likelihood is very often implicitly employed in machine learning for model selection. You just measure which model works best, you take this. What you then do is actually this. And this is quite simplistic because you could do better. But even if you don't know these a priori likelihoods, there are better ways of doing model selection, and this is what we'll quickly look into now. There are actually things called model selection criteria. There is a number of them in the appendix, so-called Bayesian information criterion or Akaike information criterion. These are numbers you can compute that tell you, given your model's performance in terms of how accurate is it, and the flexibility of the model, how well is the trade-off between the two. It basically assumes a model that is very flexible, like has a lot of capacity, lots of memory, so to say. This has to pay a price for being so wealthy with parameters. So it has to be much better than a simpler model in order to be considered a better model overall. And all these model selection criteria go back to a very important principle. That's actually the third most important thing in the lecture today, and that's called Occam's razor. William of Ockham was that guy from the 1200s, so this is really old, and if you read his original sentence in Latin, I guess, you don't directly see the connection to machine learning. But anyway, it's used a lot in machine learning as an underlying principle, which basically says we should favor, in doubt, we should favor beauty or simplicity, which is basically the same. Occam's razor says, if I have two models that perform, let's say, similarly, not exactly the same, but in the same range, but one model is much more simple than the other. Simple means less flexible, less capacity, less weights, less size of the model. Simpler. Then you should prefer the simpler model. Why? It's an axiom. There's no reason why. It's a philosophical discussion, and he wrote a book on it. In the end, you should prefer simplicity because simplicity is to be preferred. It comes down to this. There are some arguments you can make, some are really interesting, but in the end it comes down to this is an axiom of machine learning. In doubt, which model to choose, they all have similar performance, choose the simplest one. Why? Because simplicity should be preferred. There are a couple of important people in machine learning that confirmed that principle. Vladimir Vapnik, the guy who came up with the Vapnik-Chervonenkis dimension stuff in computational learning theory and the support vector machine classifier, he said, you should never try to solve a more complex problem than you need to solve. Content with a simpler thing. Einstein said, make things as simple as possible, but not simpler. And so on. You could actually see it also this way. If you have a very, very complex model that performs well to a certain degree, complex means it has lots of curves around every possible data point. You can imagine it like that as an imagination. Every special case this model has and makes for some data points is a possibility for failure. A simpler model that is just a straight line, in that example, has fewer failure cases because it's simpler. So when they both perform equally well, then go for the simpler one because you could imagine it generalizes better. That's it. What to remember? Occam's razor is a principle, and it means prefer the simpler model when they perform, let's say, in the same range. It can also mean you take a model that has a slight worse performance and is much simpler. Okay? Now imagine we have done all that we learned today. We have partitioned our data the right way, so we make the most out of it. We have measured the right figures of merit. Given that, we have evaluated a lot of hypotheses and we choose the one that looked best according to our criteria, to Occam's razor, to maximum likelihood, and so forth. Now, we are tasked with a question like, okay, is it really the best? Or is there a better one? Maybe. Still, is there a chance for a better one? Could actually the model that has 0.2% less accuracy, could that actually be better? Remember, when we measure errors, this error is just based on a sample of the data, so it has some variance on it. So it's just an estimate of the true error. It could be that our error that is actually lower for our model we picked than for other models, that this was just a happy occasion, and actually this model is in fact a little less good when I would measure the error on the complete data set. So how sure can we be that the model we picked is actually the best one? In practice, if we did cross-validation, we did almost all we can, and that's enough. We don't care if another model is maybe equally good. We found a good model. That's it. Done. If you write a paper on it and you're in the master program, so I guess you want to write 3 papers during your course of study, 1 for every project. When you want to write a paper, you have to report on novelty. You only have something to write when you can show that the thing you built is actually better than what was there before. That means you have to compare your stuff with the stuff that is out there, and you have to show that your stuff is significantly better. You really have to answer that question. Your model has provably to be better than the one before, otherwise nobody wants to read your stuff. So in case of academic research, when you really want to prove this is significantly different from what we had before, and positively different, better, then you have to do statistical tests on your measured errors in order to show they are better. We don't go into details here. I assume you can learn about statistical tests or learned about them already elsewhere. But again, in the appendix, there's a 2-pager on the recipe to calculate the so-called students test to see if your model works better. Fun fact, the guy who came up with the students t-test was actually that guy, and he worked for a brewery, and he wanted to prove which beer is better than the other. And because he didn't want to publish that under his own name, I think he was prohibited by the company he was working for, he wrote under a pseudonym called Student. And this is why the thing is called Students t-test. So it has nothing to do with that only students make these kind of tests. But often students have to do these kind of tests. And if you need a recipe how to do it, look at the appendix. We'll come to an end. In the end, lots of things could be considered with respect to what model to choose, what to evaluate, how to evaluate. I hope I gave you an understanding that the evaluation part is actually very, 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 very important when we do machine learning. Because we are in empirical science, and that means we only have any basis to argue from if we have done our evaluation in a bulletproof way. And that means no test data may leak into the training process. We report figures of merit that are comparable to what other people did, and we can in the end show that we choose a model where it makes sense to choose it. That we didn't choose an overly complex model just to squeeze out the 1 per promille of accuracy or something like that. But choose a simple, very good model that is provably better than the rest. Of course, other things play a role as well when you choose models. For example, if your data set has certain properties, like you have more columns, like more features, than you have rows in your data set, like more features and instances. That's a very specific case that really limits the number of algorithms you can use in them. Support vector machines do particularly well on these kind of data sets, like for example in bioinformatics, we'll talk about it next week. Gaussian mixture models or any other Bayesian method I know that works with probabilities explicitly. It does not work too well in two high-dimensional spaces. Imbalanced data is a problem you have to care for separately, and we didn't cover much of it here besides contingency tables and recurrent precision and stuff like that. If you have a problem like that, that probably deserves some weeks of extra looking into that and finding out what to do about it. And the solution is probably multilateral. Like you will work on, try to see, can I resample the data in order to make it appear more balanced? It may mean you have to acquire more data. It can also mean you choose specific algorithms and tune the loss functions in a way that they can cope with that. And in the end, if you want to be successful, it's a combination of those. Good. Did I say Bayesian methods don't work with imbalanced data sets? No, I said Bayesian methods don't work here. Actually, I'm not sure about all the Bayesian methods. In that case, things like Gaussian mixture models that explicitly model the probability distribution, they don't work well with large dimensions. Correct. Good. You can read the review yourself. The lab today will be on having a look at a specific form of cross-validation. So for the next 3 weeks, we will stay with the same lab. It's all the lab V04. And we will just do the first task today. There's an IPython notebook that basically has all the code already in it. You don't have to write a single line of code if you don't want to, but you can familiarize yourself with so-called IPython or Jupyter notebooks. You can let the code run, and you can find out, play a little with that bias and variance things by analyzing a specific form of cross-validation, and that's a leave one out cross-validation. That is basically, you train on all your data points except one, and on this you test. And this you do for all your data points. And you will basically find out that this is a very computationally costly method that is maybe not the best you want to do. And that's very interesting to find out. Thank you very much. See you later.